Hi, Assalamualaikum. We meet again. This is my lecture number 2 for CHM577. In my lecture 1, I stopped at this slide where I was explaining why metals lose electrons to achieve noble gas outer electron configuration, whereas on the other hand, non-metals gain electrons to achieve stable noble gas outer electron configuration. So as such, we will always find that elements that are on the first group will have a charge of +1 because they lose one electron to look like noble gases. Those in the second group will have when they become cations, they will have a charge of +2 to get to look like this noble gas. Whereas in the P group or in the P block, the elements in the third group will have a charge of +3. Elements on the seventh group will have a charge of -1 because they need to acquire one electron to look like a noble gas. In group 6, they will become an ion with -2 charge, whereas group 5 will have anions of -3 charge. So that is why you have all these electrons moving in and out of the elements just to achieve octet, really, just to achieve stability. But that concept is not new to you. So I'm going to cover next about isoelectronic. Isoelectronic means that any species that have the same number of electrons and ground state electron configuration. The examples are sodium plus has a electron configuration that looks like neon, which is 1s2, 2s2, 2p6. Aluminium 3 plus also has electron configuration of neon, and these are said to be isoelectronic, same number of electrons. And then similarly, you have 1s2, 2s2, 2p6, also neon for F minus fluoride anion, O2 minus oxide anion, and N3 minus nitride anions. So all these species, because they are all having electron configuration like neon, so they are all called isoelectronic. So that is a small quiz here that I would like you to try and discuss with your friends or try to get an answer of. What neutral atom is isoelectronic with H minus? Yeah, H minus is when hydrogen obtain one electron to make H minus, which is a hydride anion. Yeah. So what has 1s2? It's really very simple for you to answer, isn't it? Okay. Do you get helium? I hope you do. Otherwise, then you'll be in trouble. So next slide is about transition metals. So I want to cover a little bit about transition metals because transition metals have a slightly different story to representative metals. If you recall, transition metals are those elements located in the D block, whereas representative metals are those representative elements are located on the S block and the P block. Now, for transition metals, since they're all metals, so they will all become cations. It's very, very rare that you get transition metals become anions. Okay. When a cation is formed from an atom of a transition metal, electrons are always removed first from the s orbital. And after that, when the s orbitals are all empty with the ionization, barulah, then they remove electrons from the d orbital. So for example, if you have iron is argon 4s2 3d6. Now, who can sing to me the 10 elements in the first series of transition metal? So what do you have? You have scandium, titanium, vanadium, chromium, manganese. What else? Iron, cobalt, nickel, copper, and zinc. Yeah. So iron is located in here. If you look at this here, iron is there. So it's 4s2 3d 1 2 3 4 5 6 3d6. So 4s2 3d6 is iron. Yep. So iron, which is in the elemental stage or state, does not lose any electron. But when it becomes cation, it will first lose the electrons on the s orbital, on the 4s. So iron 2 plus or Fe2 plus has an electron configuration of 4s0 3d6. The s is the electrons on s is lost. So you are only left with argon 3d6. So that is iron 2 plus. And if the iron needs to further oxidize to become iron 3 plus, then you start losing electrons from the d orbital, making 4s0 3d5. Yeah, 3d5 or argon 3d5. Similarly, when manganese, which is argon 4s2 3d5, needs to lose 2 electrons to make manganese 2 plus, it will become argon 4s0. These 2 electrons here, these 2 electrons here are going to be lost and making 4s0. So 4s0 3d5 or argon 3d5. However, because half full d orbitals have a special stability. So this is the case. So 3d orbital is more stable than the 4s orbital in here. So manganese 2 plus will be 4s0 3d5. It will not be this case here. Yeah. You don't get 4s2 3d3. Now all the elements in the periodic table will have a very, very noticeable trend or behavior. It will have a similar type of behavior. Those behaviors or trends are influenced by 3 factors. The first factor is the energy level. The higher energy levels are further away from the nucleus. Obviously, like I explained earlier, all the orbitals that are located further away from the nucleus will have the higher energy level. And number 2, the second factor is the charge on the nucleus. Everybody knows that in the nucleus, we have proton and neutron, right? In the nucleus of an atom, you have protons and neutrons, whereas the electrons stay on outside in the orbitals. So in the nucleus, you have a positive charge because all protons have a positive charge, whereas neutrons are neutral. They don't have any charge. So the nucleus will be positively charged. The charge on the nucleus or the number of protons that is contained in the nucleus, we will present charges. The more charge will pull electrons closer. So if you have a lot of protons in that nucleus, the electrons outside in the orbital will be closer pulled into the closer to the nucleus. So because positive and negative obviously attract. And the third factor is the shielding effect. I'm going to tell you about the shielding effect in a while. Now, the shielding effect is what happens when the electron on the outermost energy level is being shielded or is being protected from the pull of the nucleus. Here is the nucleus. Yeah, you have the nucleus here right in the middle. So what is felt by the electrons sitting on the outermost shell is going to be less if you have a lot of um, shells inside. So this layer, that layer, and that layer will produce some kind of shielding effect. The electrons on the outermost energy level has to look through all the other energy levels to see the nucleus. So second electron has the same shielding if it is in the same period. So if you put the second electron on the outermost, what is experienced, the shielding that is experienced by that second electron on the outermost will be the same with what is experienced by the first electron. However, the shielding effect is going to be different if you are comparing the electron on the outermost with the electron that is on this layer. Oops, yeah, on that layer there, because the this one here, will have less shielding compared to the one on the outside. Yeah. So that is what is meant by the shielding effect, because the shielding effect is shielding the electrons from what is the pulling factor from the nucleus, because the nucleus is positively charged, the electrons outside are negatively charged. The more layers, the more shielding it will provide. Okay. So also about atomic size. So atomic size is about the radius. When you want to know what is the radius of an atom, you have to do this kind of uh, measurement, where the distance between nuclei of two atoms, the nucleus of this atom with the nucleus of that atom, the distance you divided by 2 is actually the atomic radius. It is half the distance between the two nuclei of a diatomic molecule. So that is the definition of atomic size or atomic radius. Okay? And what do they influence? What do these factors influence in terms of periodicity? So energy level and shielding have an effect on the group. Nuclear charge has an effect on a period. Now remember, the group is the vertical arrangement of elements in periodic table, whereas the period is the horizontal arrangement of the elements in the periodic table. So the group is very, very much affected or influenced by the the energy level and the shielding effect, whereas the period, because you move from one quantum level to another, uh, from one shell to another, by introducing another layer. So another layer will take into account nuclear charge. So nuclear charge has an effect on a period, energy level and shielding have effect on group. So you have to understand that for us to be able to discuss the next upcoming topic, that will be atomic radius. So periodic variation in physical properties. First, you have to look at the effective nuclear charge. Is it the positive charge? It is the positive charge that is felt by the electron, like I was telling you. The electron on the orbital, what they feel from the positive charge in the nucleus. Yeah. Given that the ZF Z effective is equal to Z minus sigma, where sorry, that should be a sigma. Symbol SYMBOL. Yeah, well, that's a sigma. Z minus sigma, where Z is the actual nuclear charge. Z is really quite straightforward. If you have 24 protons in your nucleus, then Z is 24. That is really easy. But sigma is the shielding or screening constant, where 0 is smaller, obviously, than sigma, but it is smaller than Z. So Z cannot be, sigma cannot be any bigger than Z. So effective charge, or ZEFF is equal to the number of actual nuclear charge minus the number of inner or core electrons. So how do we determine core electrons? Is the number of electrons in the shells that are lower than the outermost. Contohnya, example, sodium. You have sodium is 2.8.1. Yeah, that is very, very familiar to you. 2.8.1. That means that one electron is what we call the outermost electron. 2 and 8 are the core electrons. So 10. In the case of sodium, there are 10 core electrons. So it's really quite simple. Z is 11. 11 is the number of proton in the nucleus of a sodium, minus core, which is 10, the 2 plus 8, and that is actually 11 minus 10. So your ZF, your effective nuclear charge, is 1. So if you look at it, the radius of sodium is 186 angstrom. Well, this should be in angstrom. Oops, excuse me. Yeah, radius is in angstrom. Now, look at magnesium. Magnesium has 12 electrons and 12 protons. So the Z is 12, core is 10. So ZF, or the effective nuclear charge, is 2. So the higher the effective nuclear charge, the smaller your atom will be. The radius of sodium is 186. The radius of magnesium is 160. Why is that? Because the 2 electrons that is outside of magnesium, the pull that they experience from the nucleus is equivalent to 2 pull, compared to 1 pull for sodium. So if you have the 1 electron being pulled inside by the nucleus, that pull must obviously be smaller than 2. If you have, for example, 2 rubber bands pulling your electrons together, obviously it is stronger than 1 rubber band. Yeah. So when you have Z effective of 1, the pull towards the nucleus is smaller compared to 2. But when you go look into aluminium, aluminium is 13 proton minus 10 core electrons. So you get effective nuclear charge of 3. That means 3 electrons outside are experiencing a 3 plus pull towards the nucleus, a lot stronger than pull of 2 or pull of 1. So aluminium is smaller than your magnesium and your sodium. So it's actually 143 angstrom. And silicon, similarly, you have 14 minus 10, you have 4 plus charge from the nucleus, pulling 4 electrons towards the center of the atom. You are going to have an atom that is shrinking or smaller. So you have 132 angstrom. So as the number of effective nuclear charge increases, the radius or the atomic size of that particular element will become smaller. I hope that is clear. So you're looking at the trend going from left to right with the increasing effective nuclear charge. ZF is effective nuclear charge increasing. You are going to see that the size from lithium towards neon, lithium is bigger than neon. Yeah, lithium is bigger than fluorine. Lithium is bigger than oxygen because the effective nuclear charge is increasing as we go towards the right side of the periodic table. So core electrons is bigger, closer to the nucleus than valence electrons. Thus core electron shield valence electron bigger than the valence electron shield each other. Yeah. So core electron, the shielding effect of core electrons is bigger than the valence electrons shielding each other. So moving to the right across the period, core electron remains constant. In the case of lithium 2 neon, the core electron is 2, but Z increases. The added electron will be valence electrons, and due to valence electron does not shield each other, moving to the right across a period, your ZF will be felt by all the valence electrons. Your effective nuclear charge will be felt by all the valence electrons. But going down the group, when you go down the group, obviously, as the shell becomes from shell 1 to shell 2 to shell 3, shell 4, it will become bigger. Going down the group, the size will become bigger. Going to the right of the group, the size will become smaller. Okay? For example, which element's outer shell or valence electron is predicted to have the largest effective nuclear charge? Okay? Is it chloro, oxygen, nitrogen, or calcium? So the thing to do is for you to calculate. For chloro, there are 17 protons in the nucleus minus 10 core electrons is going to give you 7 effective nuclear charge. Oxygen, you have 8 minus 2, which gives you 6. Nitrogen, 7 minus 2, giving you 5. Calcium, 20 minus 18, giving you 2. So the largest effective nuclear charge among the 4 here will be your chloride. No. Chlorine, not chloride, but chlorine. Chloride is the anion. Chlorine is the atom. Yeah? Oxygen, 6. Nitrogen, 5. And calcium, 2. So obviously the biggest pull experienced by the outermost electrons will be in chlorine. And the smallest will be in calcium. Right? I hope that's clear. So the group trends, as you move from top to bottom, it will increase down the group, as I said, because the shell becomes bigger as we go down. If you look from hydrogen, which is tiny, lithium becomes slightly bigger, and underneath lithium is sodium, which is on the shell number 3. It becomes a lot bigger. Potassium on shell number 4, more big, and rubidium, which is on shell number 5, biggest. Jadi going down a group, the size increases. Going to the right in the same period is going to decrease the size because of the effective nuclear charge. I think that's not a foreign concept to you. Yeah, the atomic size will decrease across a period from the left to the right. So sodium is the biggest in the third shell. Magnesium becomes smaller, aluminium smaller, and as you go down, or as you go to the right of the periodic table, argon has the smallest atomic radius or the smallest size. Yeah. So that is within the same group, you're going to have all the group 1 element to be the biggest. Then it will start to decrease until you reach the group 7 elements. And your group 7 elements, if you take away the noble gases, the group 7 elements are the smallest. So within the same group, within the same period, group 1 is the biggest, group 7 is the smallest. Sodium is biggest, sodium is biggest, chlorine is smallest. Potassium is biggest, bromine is smallest, and so on and so forth, all the way until the 5th period. I think that's also not a concept that is foreign to you. Now, let's look at the cases were simple when we talk about atomic radius. What about ionic radius? Yeah. Now, ionic radius, anions, which are negative ions, are always larger than the neutral atom. Why is that? Because to form an ion, electrons are being added to that particular element. For example, chlorine, to become chloride, you have to add 1 electron, and the size of chloride is a lot bigger than chlorine because the additional electron that you put is going to repel each other. The repulsion force, the electron-electron repulsion force will spread the electrons further apart, making the size of this anion bigger than its parent atom. The protons cannot pull the extra electron that you put in as tightly towards the nucleus. If you remember, the proton are still the same. The number of proton in chloride and the number of proton in chlorine is still the same, but there is 1 extra electron in chloride that makes it a lot more difficult to pull the electrons within or inside in towards the nucleus, making anions always bigger than the parent atom. However, for cations, remember when you are producing cations, you throw away electrons, right? You throw away electrons, cations, they become positive ions. They are a lot smaller than their respective atoms or their respective parent atoms because, of course, when you have removed 1 electron from the outer shell, for example, sodium 281, when you remove that 1 electron on the outer shell, you're going to be left with 2.8. Obviously, it's going to shrink because 1 outer shell is removed. Yeah, there is less electron-electron repulsion because you remove that 1 extra electron. The protons in the nucleus are going to outnumber the electrons. Therefore, the protons can pull the fewer electrons toward the nucleus more effectively. So making sodium cation a lot smaller than your sodium atom, right? So next is about the ion group trends. So each step down a group is adding an energy level. If you move from lithium plus to sodium plus to potassium plus, rubidium plus, cesium plus, you're going to add 1 energy level going down from top to bottom. And obviously the same argument will follow, is going to become bigger. So lithium plus is the smallest ion in the group 1, whereas cesium plus is the biggest ion in period 1. Ions therefore get bigger as you go down because of the additional energy level. All right, so that is the trend. That is the pole, the polar of your properties. We're talking about sizes at the moment. Now, the trend of ions period, yeah? Across the period from left to right, the nuclear charge increases, yeah? So similarly, just like the when we talk about the atomic radius, when we talk about uh, anions and cations, it's still the same also. For example, lithium plus is bigger than beryllium 2 minus, bigger than boron 3 plus, bigger than carbon 4 plus, because the nuclear charge remains the same, but the electrons become less and less. Therefore, you have more pull towards the cation, so the size of the ions will become smaller. Notice that energy level changes also occur between anions and cations. Similarly with this one, nitrogen 3 minus is bigger than oxygen 2 minus, which is the smallest is fluoride 1 minus. Yeah, so that is the trend of your ions across the same period. So you can try to arrange the following atoms. Now remember, these are all atoms, not ions, in order of increasing atomic radius. So phosphorus, silicon, and nitrogen. Which one is the biggest? Which one is the smallest? So I would like you to discuss this among yourself. The strategy is from left to right across a period, there is a decrease. Moving from up to down, there is an increase. So that is the strategy. Think about it, and then have a discussion with your friends or refer to textbooks, and then give me an answer. Between phosphorus, silicon, and nitrogen, how do you arrange them in order of increasing atomic radius? So go ahead and do that later as an assignment. Okay, I would like to go next into the size of isoelectronic ions. Iso means the same. Isoelectronic means that ions having the same number of electrons, as I was telling you earlier. Aluminium 3 plus, magnesium 2 plus, sodium 1 plus, neon, fluoride, oxide, and nitride, they all have 10 electrons. So all of these are said to be isoelectronic. They all have the same electron configuration of 1s2, 2s2, 2p6. So what about their sizes? So how are you going to arrange this isoelectronic species in order of increasing radius? So can you do that? You can have discussion about that. Oh, it's here. It's here in the answer is here. So aluminium, aluminum 3 plus, the effective nuclear charge is 13. Magnesium effective nuclear charge is 12. Sodium is 11. But they are all isoelectronic. The number of electrons outside are the same. So the bigger the nuclear charge, the more pull it will exert on the electrons outside. So you have the most number of charges or nuclear charge is for aluminium, but the same number of electrons outside. So aluminium 3 plus is the smallest, followed by magnesium 2 plus, sodium plus. And then neon has 10. Oh, 10 electrons? Really? Oh, yes, correct. Because these are from the third period. These all are from the second period. Yeah. 10 electrons, 9, 10 nucleus in the 10 protons in the nucleus, 9 protons in the nucleus, 8 and 7. So this is how the sizes of this species will look comparative to one another. you go from the smallest of aluminium 3 plus to the biggest of nitrogen 3 minus, right? So you can start comparing between nitrogen 3 minus and fluoride minus, magnesium 2 plus with calcium 2 plus. Again, I would like you to give me the answer and think about if they are isoelectronic, are they in the same group, are they in the same period. Think about all this and then decide which one between N3 plus and F minus is bigger, between Mg2 plus and calcium 2 plus, which one is bigger. So you can apply what we have discussed before in answering these quiz questions. Right. Now, I'm going to go into the last topic of today's lecture, which is ionization. No, not the last topic because we have electron affinity. Okay, ionization energy. Ionization energy, I'm sure you have found it before or you have encountered this term before. It is the minimum energy in kilojoule per mole that is required to remove an electron from a gaseous atom in its ground state. And the size or the magnitude of ionization energy depends on how tightly is the electron held onto the atom. And how tightly is the electron held onto the atom depends on the nuclear charge. So you really have to understand the nuclear charge. Yeah. So if you have, for example, X, yeah, X in gaseous form to make X plus electrons. That means removing one electron from your gaseous X. One electron, that means I1 is first ionization energy. Now, if you have X, remove this should be X plus. I'm sorry, this should be X plus. Yeah, I'm sorry about that. There's some typo error here. So make sure you correct your typo error, please. Oh, wow, I can't find superscript. What is superscript? Yeah, that's it. Yeah, that when X plus loses, oh, sorry. There you go. Right. When X plus loses another electron to make X2 plus, that is the second ionization energy. And when X2 plus loses, oh, still the typo error here. Okay. Paste. Right, let me make it longer and move it along that way. Yeah. When X2 plus loses another electron to make X3 plus, then that energy required to do that is called the third ionization energy. And it is always easier to remove the first electron compared to the second electron compared to the third electron. Why is that? Because the first electron is the furthest away from the nucleus. Yeah, the further away it is from the nucleus, the easier it is to remove it. So after you remove the first electron, the second electron that is located closer to the nucleus will be slightly more difficult to remove, will require more energy to be removed. And then the third electron, which is even closer to the nucleus, will also be a lot more difficult to remove. So first ionization energy, second ionization energy, and third ionization energy. The higher the ionization energy, the more difficult it is to remove the electron. So that's not something that is not logical. It is very logical. Now, going down a group, when you go from, for example, lithium to sodium and so on and so forth, the first ionization energy will decrease. Why would it decrease? Because remember size. The bigger the size, the easier it is. The bigger the size of an atom, the further is the electron, the outer electron from the nucleus, the more easier it is to be removed. That is the principle. The closest electron will be difficult to remove. The furthest electron will be easiest to remove. Closest to the nucleus, difficult. Furthest from the nucleus, easy. Yeah. Electrons are further away from the nucleus. There is more shielding. Yes, obviously. The further away is the electron from the nucleus, the more shielding it is experiencing, it is easier to remove it. Now, if you go across, if you go across a period from the left to the right of a periodic table, the first ionization energy increases. Why is that? Remember the size again. We already understand that the sizes will decrease when you move from left to right. Similarly, ionization energy will increase. The smaller the size of the atom, the more difficult it is to remove the electrons from it. Yeah, the atomic radius decreases. The outer electrons are closer to the nucleus and more strongly attracted to the center because it's smaller. It still experiences the same shielding effect. It is always more difficult to remove electrons from the smaller right-hand side elements of the periodic table. So that is about the ionization energy. So when you go from hydrogen to helium, this is the first two elements that are located in shell number 1. Hydrogen is a lot easier to remove its electron compared to helium. Helium and any other noble gases, they are extremely stable. You would find that it is quite impossible for you to remove electrons from any noble gases because they have full electrons already. All the orbitals are full and none of them are free to be removed. So helium, neon, argon, those are all very stable and they will always have the highest ionization energy. And the lowest ionization energy will be your first period of your first group because they are the biggest. So going down, so lithium is the smallest, beryllium. Why is beryllium very high? Because that is the paired electron. Why is boron slightly lower than beryllium? Because that is the first electron in the p orbital. It is a unpaired electron. Remember, this is the unpaired electron. Easy to remove. There is no pairing. Again, the same. And then when it starts to pair, it starts to be difficult to remove again, and so on and so forth. So all this variation in first ionization energy, how much energy is needed to remove the first electron is really, really easily explainable when you understand how electrons are being arranged in those elements. Okay? Now, exception to first ionization energy trend, you will always have S2 to be more difficult to remove than P1, as I was telling you about the beryllium and the boron. Yeah. The removing the electron from beryllium is always more difficult than it is to remove from boron because the energy of an electron in the p orbital is greater than the s orbital because the p orbitals are slightly outside compared to the s orbital. Less energy is needed to remove the first electron in a p orbital than it is to remove it from the s orbital. And the second exception is P3 is always bigger than your P4. That's your P3, your nitrogen over there. Can you see it? Yep, that in here, there. Oh, excuse me. Yeah, that's your P3. That's your P3. But this is your P4. Yeah, P4. P4 is easier to remove than P3. Yeah, for the same reason. After the separate degenerate orbital, when we talk about degenerate means that they are of the same energy level. Okay, degenerate means that those orbitals are located at the same energy level. Separate degenerate orbitals have been filled with single electrons. The fourth electron must be paired. Yeah, obviously, one in the px, one in the py, another one in the pz. Once they are all singly occupied, you start to pair up. The fourth one go here. The fourth electron is paired. Electron repulsion make it easier to remove the electrons from the paired one because they repel one another. So when they repel one another, it's easier to remove that fourth p or electrons. Yeah, that is in the Hans rule. Right? The second and higher ionization energy, the definition, the second ionization energy is the energy required to remove a second outermost electron from the ground state atom. Subsequent ionization energies increase greatly because an ion has reached the state like that of a noble gas. So always second ionization energy is always higher than your first. Third is always higher than your second. So for elements that have reached filled or half-filled orbital by removing 2 electrons, the second ionization energy is lower than expected. Yep. So these are the ionization energies of hydrogen, helium, all the way up to neon. You will find that hydrogen is the lowest compared to helium. And then when you start to lithium, this is a numerical presentation of the graph that we see here. Where are they? Excuse me. Graph that we see here. Yeah. I'm thinking about this one. Yeah, that one over there. The smaller the element, the more difficult to remove the electrons, the higher the ionization energy. So it is inversely proportional. So you're going to have these numbers inversely proportional to the size. The small atoms will have high ionization energy. And the second is higher than the first. So that's the trend. So like what I was explaining earlier. So what are the factors that determine ionization energy? The greater the nuclear charge, the greater ionization energy, obviously. The greater the distance from nucleus, the easiest it is for you to remove. So decrease the ionization energy. Field means full. Huh? When S field is 2. When P field is 6 electrons because there are 3 orbitals. Full p orbitals contain 6 electrons. Half full p orbitals contain 3 electrons. So filled and half filled orbitals have lower energy. So achieving to remove them is easy. Lower ionization energy. And we also have to talk about the shielding effect. You all understand what is the shielding effect by now. Now, last topic in this lecture, I'm on 48 minutes. It's not going to take me long. Electron affinity. Now, electron affinity is the negative of energy change that occurs when electron is accepted by an atom in the gaseous state to form an anion. So what does it mean? So, when you have X in the gaseous phase receiving an electron, it becomes X minus in the gaseous phase. For example, fluorine receiving an electron becomes fluoride. So your enthalpy H is minus 328 kilojoule per mole. To put 1 electron into that fluorine is actually a negative expenditure of energy. That means When you pull electrons, you require energy. When you put electrons in, it will create energy. So energy released will be 328 kilojoule per mole. So the electron affinity is the reverse of that. Yeah, electron affinity is plus 328 kilojoule per mole. So for oxygen, you have the delta H enthalpy, the enthalpy change of the adding electron into your oxygen is minus 141. So electron affinity is plus 141. Electron affinity is really defined is how much that particular element loves electron. The higher electron affinity, the more that element like electron. For example, fluoride really loves electrons because it has very high electron affinity. Affin means love. Yeah, the love for electron. Oxygen has lower electron affinity than fluorine because the electron affinity for oxygen is lower than the electron affinity of fluorine. Yep. So it is actually the energy given off when a neutral atom in the gas phase gains an extra electron to form a negatively charged ion. So going down the group, electron affinity decreases. Why is that? Because the size becomes bigger. When the size becomes bigger, the nuclear charge is less felt. So you want to add more electrons to it, it's not going to be very easy. So the liking of potassium to electron is a lot less than hydrogen. Going across a period, the electron affinity becomes bigger. Fluorine has the highest electron affinity. So electron affinity increases to the right and to the top, going up and to the right. So electron affinity of fluorine is the biggest of them all. Yeah. And the electron affinity of potassium is smallest. So that is how you define. Exception to electron affinity trend, non-metal elements in the first period have lower electron affinities than the elements below them in their respective group. Yeah. So non-metals will always have lower electron affinities compared to the elements below them. Elements with electron configuration of S2, P3, and P6, that means full and half full orbitals, have electron affinities less than 0 because they are unusually stable. Yeah, because very stable. When the S orbital is full with S2, or when the p orbital is half full with with P3, or when the p orbital is very full with P6, they are going to have very high stability. So when they have high stability, it is really difficult to give them more electrons. They're quite happy, existing as they are. So there's no need for you to give them electrons. So beryllium, sodium, and neon, beryllium, nitrogen, and neon, they have quite low electron affinity because electron affinity are all much smaller than ionization energies. S2 it has less than 0 electron affinity, very stable, diamagnetic atom, no unpaired electrons. P3 also stable, P6 also very stable. So no need. They have no need for any electrons. So they don't really like electrons. So that is about electron affinity. So this is the graph of your electron affinity. As you can see here, fluorine has the highest electron affinity. Can you see it? Yeah, the highest electron affinity. Going across from hydrogen to fluorine. And when you go across the period on the periodic table, From fluorine going down into astatine down here, fluorine is still the highest, oxygen is still also the highest compared to your polonium. Yep, that's about electron affinity. So electron affinity versus atomic number, this is the graph, and all this, you can see that the halogen groups are the highest of them all in terms of electron affinity. They are they really like electrons. Halogens really love electrons, right? And all of this, you can read the actual reasons uh, intimately from any textbook that you have with you. So this is the trend for electron affinity. So with that, I have completed lecture 2. So thank you very much, and I hope all this rushing through the topics is not going to puzzle you too much. If you have any question, please send them to me after you read the textbook or after you discuss with your friends. So that's it, guys. Thank you for listening in for my lecture 2. Bye-bye.